Okay, so now we've talked about sample proportions with our categorical data. We're going to go ahead and talk about the sampling distribution for means. And so sample means with our quantitative data. So we are going to look at, we have our population distribution right here. And as we can tell, our population distribution is right skewed. It has a mean or a center right around 80,000. And it has a range, because that's all I can really tell from here, from 0 to about 250,000. So a range of $250,000. Even though it's skewed, there's no real big distinct outliers that we can see at this point. But now when we look over at our sampling distribution, all of a sudden it looks a little different. Now these are sample sizes of 100. So we took all the possible sample sizes of 100 and we graphed the means for each one of them. And so now we're getting a distribution that is pretty symmetrical. And the mean of the sampling distribution actually ends up being right about that 80,000 also. So the mean of our sampling distribution ends up being about 80,000. And then when we look at our range, because I can't really calculate standard deviation at this point, but our range is looking at like 50,000 to 100,000. So now we have a much smaller range, or a much smaller spread, which kind of goes into the idea of, with our sampling distributions, we're going to have a smaller standard deviation, a smaller spread than even our population distribution. And of course, it doesn't look like there's any outliers. And so what is this really telling us? This is telling us that when we are looking at our sampling distribution, so many random samples from a population, the sampling distribution of the sample mean is centered at the population mean. So we have that same center of that 80,000. So the mean of our sampling distribution should be the mean of our population. And that seemed pretty accurate from our previous example. Now our standard deviation is actually going to be smaller. So this spread is smaller. So what actually ends up happening is the standard deviation of our sampling distribution ends up being the standard deviation of the original population divided by the square root of our sample size. And so as our sample size gets bigger, that sampling distribution standard deviation gets smaller. But again, we're still looking at that 10% condition. So either we're sampling with replacement, or if we're sampling without replacement, we're looking at that 10% condition. Now, it doesn't matter what the shape of our original standard distribution is. This will be true no matter what. So if our original standard, or if our original population distribution was skewed, it's still going to have this information. So suppose that the number of movies viewed by students in the last year by high school students has an average of 19.3 movies with a standard deviation of 15.8. Suppose we were to take a simple random sample of 100 students and calculate the mean number of movies viewed by the members of the sample. What is the mean of the sampling distribution? So by our rules, the mean of our sampling distribution should equal the mean of our population distribution, which is 19.3 movies. What is the standard deviation of the sampling distribution? Check whether the 10% condition is satisfied. So we probably didn't choose with replacement. So to check our 10% condition, is it reasonable to assume that there are more than 10 times our sample size? So 10 times 100 is 1,000. It's reasonable to assume that there's more than 1,000 high school students. Yeah, there's more than 1,000 high school students at this high school. And then we can calculate that standard deviation. The standard deviation of our sampling distribution should be our standard deviation divided by the square root of our sample. So our current standard deviation is 15.8 over the square root of the sample, 100, which is really just 15.8 divided by 10, which gives us a standard deviation of 1.58. Okay, another fact for us, the sampling distribution of a sample mean from a normal population. So if our original population distribution is normal, then what ends up happening is a sampling distribution will also be normal. And it's still going to have that mean and that standard deviation as long as that 10% condition is met. And so again, this is going to be true no matter what our sample size is. So we have no sample size restrictions if the original population distribution is normal, which is really nice. So sample problem. The length of human pregnancies from conception to birth varies according to a distribution that is approximately normal, with a mean of 266 days and a standard deviation of 16 days. Find the probability that a randomly chosen pregnant woman has a pregnancy that lasts more than 270 days. So remember, it's normal, so normal CDF. Our lower bound would be 270. Our upper bound needs to be something just really big, because it has to be more than 270, so we want it to be way bigger than any value in our normal distribution, so something like 400. Our mean is 266, and our standard deviation is 16. Why is our standard deviation 16? Because we're not taking a sample. We're just looking at the original population distribution and calculating our normal from there. So now I'm going to go into my distribution menu, enter in my information. So 270, 400, 266, and 16. And we get a 0.40129, or 3, because we try to keep those to about 4 decimal places. So for the next part, now we're taking a sample. So now we have a simple random sample of 6 pregnant women. So now our mean is still going to be 266 for our sampling distribution, but our standard deviation is now going to change. It's now going to be that 16 divided by the square root of 6. So what is the mean of the sampling distribution? Oh, the mean of our sampling distribution should be the same as the mean of our population, 266. What is the standard deviation? Is the 10% condition met? Well, let's look at the 10% condition. Is it reasonable to assume that there's more than 60 pregnant women? Yes. And so that allows us to calculate the standard deviation of our sampling distribution, which should be that 16 over the square root of 6. Which is 6.53197267. Again, using as many decimals as possible to minimize that rounding error. Find the probability of the mean pregnancy length for women in the sample exceeds 270 days. So now we're talking about the probability in the sample. So now we're using that sampling distribution information. So again, a normal CDF. Our lower bound is going to be like before, 270. Upper bound like before, 400. Mean, 266. Whoops. And our standard deviation is going to be standard deviation of the sampling distribution, which is smaller. It's 6.53197, so on and so forth. And so now we can plug that into our calculator. And we get a probability much smaller, 0.2701. And so when we're looking at this, why is this probability smaller? Because remember that sampling distribution, how that spread was much smaller and it was all very narrow and stuff like that, which means that we actually have a lower probability because of that lower spread. So everything's much more bunched up, and there's a less of a likelihood of something occurring outside of there. Okay, next problem. The height of young women follows a normal distribution. So again, if we're starting with normal, we could do all of our probabilities with the normal CDF with a mean of 64.5 inches and a standard deviation of 2.5 inches. Find the probability that a randomly selected young woman is taller than 66.5 inches. So again, a normal CDF. We have a lower bound of 66.5, an upper bound of something really tall, so 100 inches. Our mean is 64.5, and our standard deviation is 2.5. Why did I not change that standard deviation? Because this is not the probability of a sample. This is not part of the sampling distribution. This is just part of the population distribution. So 66.5, 100, 64.5, and 2.5, which gives us a probability of 0.21185. So I round that. And then our last one now is find the probability of the mean height of a simple random sample of 10 young women. So now we're doing the sampling distribution. So now all of a sudden we're going to have the normal CDF. Just like before, the only thing that's going to change is that standard deviation, because now of our sampling distribution, this thins up and becomes way more normal and less spread, just like we saw earlier. So our lower bound, again, 66.5. Our upper bound, 100. Our mean, 64.5. And now our standard deviation is going to be that 2.5 divided by the square root of 10. Now what's nice is a lot of times if you have the 84, you can type it in just like that instead of having to calculate it separate. So normal CDF, everything's the same except for that standard deviation, which is 2.5 divided by the square root of 10. And so this gives us a way different probability. So if you're not careful, you're going to end up calculating your probability wrong. So read your question carefully. Are you doing probability of the sampling distribution or just the regular population distribution?